No. Okay, what we're doing today is reviewing for test 4. This is what's going to be on test 4. Okay, and I have a lecture on every one of these I'm going to talk about in a little while. And basically, molar mass conversions. Molar mass conversions are like saying 5 grams of water is how many moles. 5 grams of water is how many water molecules. 5 grams of water is how many, if it was gaseous, how many liters. That's what I mean by mole conversions. Now, there's no chemical reaction going on, so there's no need, so you don't have to have that step 1 where you balance the equation. Okay, always sig figs. Number of molecules, remember that's Avogadro's number, 6.02 times 10 to the 23rd. I'm going to give examples of all these as well. When you have a chemical reaction, you have to balance it. And we talked about single and double replacement reactions. Number 1 is the single replacement's got the activity chart. Double replacement, sometimes there is a precipitate or a solid, sometimes there's not. And you need to be able to write out the equations for those. And then lastly is stoichiometry. And stoichiometry is like I have 15 grams of methane burning. How much water is produced? And that basically takes in number 1, 2, 3, 4 is in number 6. Now what I'm going to do is I'm going to go through and I'm going to do examples on every one of these tonight. So the purpose of tonight is to go through problems like you'll see next Tuesday. Okay. Okay, so let's go through some of these here. Okay, how many molecules are in 1.23 moles of water? Okay, remember molecules, how many? So when you're thinking of how many, I want you to think of Avogadro's number, the 602 times 10 to the 23rd. It's just like dozen. There's always 12 in a dozen, no matter what it is, whether it's eggs or chickens or ducks or students, 12, it's always 12. Avogadro's number is the same way. It's 602 times 10 to the 23rd, always. Doesn't matter what we're talking about. In chemistry and physics, normally what we're talking about are atoms and molecules. Okay, so okay, we always put what's given on the left. What we're trying to calculate on the right. Okay, so we're going to be using Avogadro's number here. We always want to make sure that we have unit cancellation going on, so we're left with what we're trying to calculate. Okay, so that's a setup. On Tuesday, you would get 90% if you just write this here. So if this problem's worth 10 points, you get 9 points for just doing this without picking up your calculator at all. All right, so what are we looking at here? We have okay, we have 3 sig figs and 3 sig figs. So obviously our answer is going to be 3 sig figs. Okay, that's probably going to be the easiest problem you're going to have on Tuesday. Is one like this, a one-step conversion. So just make sure you do all the easy ones and get full credit on the easy ones. It's like there are hard points and easy points on all tests. Make sure you get all the easy points. Don't leave any of them. Now, what I suggest you do is do all the setups first to make sure you have enough time, because you can get 90% of just with a setup. So if you do all the setups first, then go back and work them. That's a good way to maximize your points. All right. Let's do one that's a little more sophisticated. How many atoms of hydrogen are in 1.23 moles of water? Okay, how many atoms? Again, we're counting. That means it's going to be Avogadro's number. So the first thing we need to do is convert it to the number of molecules. Then from there, we're going to convert the molecules to hydrogen atoms. There are 2 hydrogens per molecule. Okay, 90% right there. Notice our moles cancel, our molecules cancel, leaves us with the number of hydrogen atoms. So the answer is going to be okay. Are these making sense? Did you ever get that worksheet we've been talking about? I've sent you it twice because you sent it via Canvas messaging, which attachments are hard. Okay, send me another message and say, please bring the worksheet Thursday.
Yeah, I sent you an email, like directly from email. And I never got anything back from that.
Anyway, I'll just give you this stupid thing. All right. Okay, this problem here is exactly like the other ones. Okay. And this is exactly like the other ones. Okay, so here we're starting with molecules. Now, and we're going to, how much does it weigh? Whenever you think weigh, you're thinking grams or mass, okay? So we have so many molecules of water. What does it weigh? Now, there's no direct one step here because there's no conversion factor that has a number of atoms or molecules and mass in one conversion. That means it's 2 or more steps. Always, and then whenever you're working with multiple steps, always think convert to moles. Convert to moles all the time. You'll find as a common thread, moles are in everything. Okay, so we're going to start with we're going to start with moles. Now, because molecules cancel, we're left with moles. Now we're going to go from moles to mass. Now, mass per mole we get from the periodic table. That means we need 2 hydrogens, 1 oxygen. Hydrogens are 101 apiece, so that's 202. Huh? Yes. Oxygen is 16. Okay, so remember, we always have the inverse of the conversion factor. But to get our units to cancel, moles is going to be in the bottom. So that means it's going to be 1802 grams per mole. Okay, this nets you 90%, doing no calculations. So we have 3 sig figs, 3 sig figs, 4 sig figs. Our answer is going to have how many? 3. So that's a big number. So that's a lot of water. Okay, so those are typical problems. I'm going to do one more for you just as an example. I want to know how many H atoms. Okay, so we have no direct conversion. So we have to go through moles. So we need to go from grams to moles using the molar mass from the periodic table. And remember the 18.02s, we just add up the H's and the O's for water from the periodic table. Now we're not using, we are using this one. I always round everything to 2 decimal places. Okay, so that gets us to moles. It doesn't get us to the number of atoms. So now we've got to convert to the number of molecules, because the 1802 corresponds to the molecule, not the H atoms. Okay, so when we do a 602 number here, we're going to get the number of water molecules. Now we have water molecules. Now we want H atoms, which is another conversion. Okay, so that's probably going to be the trickiest conversion you're going to get, is this last one. And we can start with gaseous liters. Remember, there are 22.4 liters of any gas at all, in 1 mole, as long as it's at standard temperature and pressure. Now we get into gases, we're going to talk about, well, what if it's not at standard temperature and pressure? Well, then there's a nice little conversion to do for that. Okay. All right, so let's go on now to, are there any questions about any of these you've done so far? You guys are busy taking notes and not mentioning any questions here. All right. Okay, you're gonna have to balance some equations as well. Yeah.
We're asked how many like atoms, right? The equation, the 6.02 goes on the top, so we were trying to find the weight that goes on the bottom.
It depends on your setup. Remember, you always want things to cancel out except what you're trying to calculate. That makes sense? Always do unit cancellation. It will always work, always. It's really a good technique. All right, so with chemical equations, what we're talking about when we balance them is just taking inventory on both sides and making sure they're even. All right, so let's do one. Let's do, let's take hexane. No, let's do gasoline. Okay, so gasoline is mostly made up of octane and benzene. There's a whole bunch of other stuff in it, but those are the 2 major parts. So let's assuming our gasoline is all octane. Okay, octane is C8H (18). Okay. So whenever we combust anything, we always get carbon dioxide and water. So tomorrow morning, when you start your car, I want you to run around you start it and run around the back and look at the tailpipe, and you'll see water dripping from it, because water is a product of combustion. After a while, you're not going to see the water anymore. Why? Yeah, it turns to steam. It's still there. It's just in gaseous form, but it's always there. When you see a jet fly over, what comes out the back of that jet up really up? It's called a contrail. What is a contrail? Yeah, and what are those? Not the gas in the atmosphere, but the gases coming out the back of that jet engine. What do you think they are? Huh? Burnt fuel, right? Okay, this is what jet fuel is. Kerosene, basically. There's JP4. There's a whole bunch of different kinds of jet fuel, but basically it's kerosene, which is C18H38. Okay, look at the difference between these 2. What's the difference between that and that? More carbons and hydrogens, right? When you burn carbons and hydrogens, you get what? Water and CO2. So let's go back to the jet now. Jet's burning kerosene now. So what does it produce? Carbon dioxide and water. And jets fly at 500 feet. Yeah, they're way the heck up there. They fly upwards of like 34-ish thousand feet. On it depends on the wind, yeah, the wind factor and a whole bunch of junk. But the bottom line is it cold up there? Yeah, it's very cold up there. I mean, it's like super cold. Well, what happens when you get water? Yeah. You get really cold water, it freezes. And what does a frozen water look like? What color is it? White. So what's coming out of the jet is frozen water. That's what a contrail is. Frozen water. Yeah.
So are we supposed to be balancing that equation, or is that actually balanced at the bottom?
We're gonna balance the top one here. Well, is it balanced? I mean, 8 C's here. How many C's are over here?
None.
1. So automatically it's not balanced.
Yeah, but I mean, the top one I can already tell is balanced.
No. Oh, yes, it is. That's right. Yes.
But it's the bottom one that I'm more like trying to figure out, because C8, H18, and then gotta fix that.
Well, we're not going to do this. We're going to balance this one here. We're going to balance the car one, gasoline. In fact, one of my take-home questions was, in a past test, was if a jet takes off from Seattle and flies to LA, takes 2.5 hours, and they burn so many pounds of fuel per hour, how much water do they make? How much ice do they make? So you have to figure out fuel flow times time gives the amount of fuel. Fuel is JP40 or jet fuel, which is C18, H38, and then they converted it in. Okay, so let's do this now here. All right, so first off, you ask yourself, is this balanced? Okay, easy way to tell this is not balanced is because we have 8 C's on the left, 1 C on the right. So immediately, we know it's not balanced. And what are we going to put in front of the CO2 to immediately get 8? 8. Okay. Hydrogen's on the left. We have 18. How many on the right? What do we multiply 2 by to get 18? Okay. Now let's look at oxygen. Okay, 2 on the left and a S load on the right. Okay, we've got 16 oxygens plus 9 is 25. Okay. Now the problem with 25 is we have on the left, oxygen always comes in pairs if it's a gas. So what do we multiply 2 by to get 25? 12.5 or 25 halves. Okay, does everyone see where that came from? Okay, now let me tell you a hint. Whenever we have an even number of carbons, it's always fractions. We have an odd number, it's never fractions. Okay, so are we done? Can't have fractions, so how do we clear them? Yeah, multiply everything by 2. So we're looking at so it's going to be 16, 16, 36, 36, 50 oxygens and 50 oxygens. So I'm going to give you a couple equations to balance. Now I want to do this one because we have a common ion on both sides. So we're not going to treat S's and O's. We're going to treat it the SO4 as a unit. We're going to group it together.
That's C or CU.
Cu, copper on both sides. Now, this technique of grouping only works if it's on both sides of the equation. If it's not on both sides of the equation, then you have to tear it apart. How many S's and O4s? Now, right now, the SO4 oxygens are not part of the other oxygens. The S's are not part of anything else. They're a group and they're treated like a group. Think of it like X. Okay, so copper on the left is 1, copper on the right, 1. 2 Cls, 2 Cls. 2 hydrogens, 2 hydrogens. 1 SO4, 1 SO4. So that's balanced. Okay. So whenever you, and you don't have to do it this way, you can pull apart the S's and the O's. That works fine too. It's just sometimes it can be extremely detailed if you don't do that. Okay, so that's balanced equations. You need to know about the 4 kinds of equations, 4 kinds of reactions. 1 and 2 are the same, just inverses of one another. So synthesis or combination, we put 2 things together, get a third. Decomposition is the opposite. We have something complicated, it breaks apart into 2 parts or more. It could break up into 10 parts. Bottom line is it breaks up. Number 1 is things come together. Synthesis, decomposition. Now the other 2 reactions are much trickier. Number 3, we have a single replacement, and that involves usually 99% of the time a metal. And it creates another metal. So we have a metal and an ionic compound, and it produces another metal and ionic compound. And what happens, the A and the B swap. They exchange electrons. And the question is, will this reaction happen? Okay, so say we have lead and silver sulfate. Okay, so we have a metal and an ionic solution. Question is, will the lead substitute for the silver? There we need the activity series. I'm going to give you that for the test. No, I'm not going to be memorizing that. Okay, so if the lead is higher, it'll do it. If it's lower, it won't. So the metal, not the ion, the metal has to be higher. If the metal is higher, it happens. If it's lower, it won't happen. So what we do is we find the lead and the silver. Notice the lead is higher. That means it's going to substitute. These were swapped, it would not. So if they swap, then the lead takes the place of the silver and the silver takes the place of the lead. Now, we have to make sure everything is balanced. I'm going to give you that ion chart I passed out. You know that silver is a +1, sulfate is a -2. That's why we have to have 2 silvers to balance out the -2 sulfate. On the right, we have that. Now, lead can come as a +4 or a +2 on your ion chart. So we know it's a +2 because there's only one of them here against one SO4. The SO4 is -2. If this was a +4, we'd have to have two of these to get it up to -4. So make sure everything's balanced here, okay? So it's not balanced yet because we need to balance out. We've got 2 silvers. That means we have to have 2 silvers on the right side as well. Hence the 2 there. So now it's balanced. So all chemical equations, no exceptions, have to make sure they're balanced. And 99.9% of the time, I will not give you a balanced equation. So any equation from me, assume is unbalanced. Okay, so that's a typical single replacement. Now, let's look at another example. Okay. Will the copper replace the lead? So what you're going to do, you're going to find the copper and the lead. And is the copper above or below the lead? Below. So it can't replace it. It has to be above it. So what happens here, we just put no reaction. Nothing will happen. Okay, so those are 2 situations with single replacement. The metal, the one on metal on the left has to be above the other one. If it is, it happens. If it's not, it won't happen. Black or white. Okay, so let's go to double replacement now. Now, double replacement, instead of one being replaced, they're both replaced. So silver nitrate, sodium chloride. Okay. Notice there's no metal, they're all ions. So whenever you see a metal, think single replacement. No metals, think double replacement. Okay, the question is, when these swap, the cations swap, it will become silver chloride and sodium nitrate. Now the question is, will either one of those form a solid? That's where this comes in, this chart here, which I'm going to give you on Tuesday. So we find chloride, we find silver, black, that means it's a solid. So this becomes a solid. Sodium nitrate, nitrate and sodium white. That means it stays ionic. So that's an AQ, that's supposed to be an AQ there. Looks like a Q, but it's AQ. AQ stands for aqueous. That means the water has taken apart the molecule. So and then of course, is it balanced? Yes, balanced. Okay. So this is considered the molecular equation. That means everything is in molecules. The total ionic equation is we break everything apart into individual ions. So that means the silver and the NO3 come apart. the NO3 comes apart. The sodium comes apart. And then we have the same double swap. So we end up with, now on a total ionic, if it forms a solid, liquid, or gas, it's together. If it's an AQ, it's apart. So the AQ here now we have to, those are apart. So that's the total ionic equation. So the total has all the ions all split up. And that's the part that's tricky because there's so many little details. It's simple in concept, but it's just got a zillion parts. That's why they're kind of tricky. Now, when you look at the total ionic equation, are there ions on both sides of the equation that are aqueous? Well, we have NO3. What did I do wrong here? This should be NO3, not Cl. Okay, so we have NO3, NO3. We have sodium and sodium. If it appears on both sides of the equation, that means it's not doing anything. So those are called spectator ions. And then what's left over is going to be the net ionic equation. In other words, if something happens, that's when you net equation. In this case, a solids formed, the silver chloride formed. So hence we have a net ionic equation. If nothing happens, then we don't have anything going on here. So something's got to happen before we have a net ionic equation. You can write NR. I usually put null set here. There's a lot of ways to do it. Just make sure that you communicate to me as to that nothing's going on. If I ask you for the spectator ions, those are the ones that appear on both sides. Na and the nitrate. Now, again, I've got tons of worksheets under files to practice all these, plus answers. Okay. Now let's go on to stoichiometry. Stoichiometry is the quantitative relationship between all the constituents. Quantitative means math. So in other words, what's the mathematical relationship between the chemical constituents? Okay, a typical problem, let me erase. Okay, so for example, 15 grams of methane burns in oxygen, produce water and carbon dioxide. How much water is to produce? Okay, so we go through our 4 steps. Is there a chemical reaction going on? Yes. So what's step 1 then? Always balance it, right? Is this balanced as written? Okay, we need to balance it. Okay, it's now balanced. Step number 2, what's given? Exactly, 15 grams of methane. So that goes on the left. And what are we trying to calculate? Yeah, how much means grams. So we want grams of water produced. That goes on the right. Now the setup. Remember, there are 3 parts to the setup all the time. Step 1 is to get what you're given to moles. How do we go from grams to moles? Molar mass, right, from the periodic table, not the 6.02. Okay, so grams to moles comes from periodic table. That's the decimal number on the periodic table. And it's okay, so now we have moles. So step 1 is to get what you're given to moles. The middle step is the conversion from what you're starting with, CH4, to what you're ending with, water, via the coefficients from the balanced equation. That's why we balance an equation. So for this to cancel, the CH4 has got to be on the bottom. Okay, and we look at the coefficients. There's a 2 for the water, 1 for the methane. And notice the methane now cancels. All right, now we go from, so that's from the balanced equation. Now we go from moles of water to grams of water. So that's going to be 1802 per mole. Okay, so we have, so everything cancels except for grams of water. What are we trying to calculate? Grams of water. Now, every stoichiometry problem is going to have at least 3 steps. So when you set these up, make sure you've got 3 steps. Could be 4, maybe a little conversion to kilograms or something like that. They have to have these 3 basic steps. So we're trying to cake. First step is given to moles. Second step is the ratio from the balanced equation. The last step is converting moles to what we're trying to calculate. It could be we're trying to calculate liters of gas. Could we might be calculating number of molecules or something, but we're going from moles to whatever that is for step 3. Step 1 is we're taking whatever we start with and converting it to moles. And again, this is going to be 90% credit. So how many sig figs are we talking about here? That's 1503. So 33.7 grams. Now that's the most straightforward stoichiometry problem. I call it a mass to mass stoichiometry problem. Starting with mass or ending with mass. But because it's a different molecule, that's why we have to use the balanced equation. When we first started off tonight, nothing was happening. We were just converting something. It's like renaming something. So there was no chemistry going on. But whenever there's chemistry going on, then you've got to involve a balanced equation and have that middle step. Okay. Let's stick with this reaction. So we're starting with this one, 29 grams of carbon dioxide is produced. How much oxygen is consumed? Now notice what we're starting with is on the right of the equation. What we're going to end up with is on the left of the equation. Okay. So the equation doesn't determine what's given. The data that's given to you determines what's given. Okay, so on the left is going to be what? Yes. All right, and what are we calculating? No, it doesn't matter. Gas weighs, and it also occupies volume. Okay, so how much means what? Grams. Okay, so step number one is grams to moles. We want the grams to cancel. So we need to take carbon dioxide. Carbon is 1201. Oxygen is 16 twice. So that's 32. Okay, it's a standard step given to moles. Step number two, the middle one, is the ratio from the balanced equation. Okay, so we want carbon on the bottom, carbon dioxide on the bottom, and oxygen on the top, because the carbons need to cancel. And from the balanced equation, it's 1 to 2. Looking at the coefficients now. Now we're going to convert moles of oxygen to grams of oxygen. And it's going to be 3 sig figs. Now, notice this one here. We have liters. Now we're going to get 2 liters in this class. One's gaseous, one's liquid. So is this a gaseous or a liquid liter?
Yes.
Gas. So if it's gas, we're going to use the 22.4. If it's liters, that's another calculation we're going to do in unit 5. Okay, so it's 22.4 liters per mole. Okay. So what's given? Oxygen. Okay. So going from liters to moles for gas at standard temperature and pressure, it's 22.4. That gives us 2 moles of oxygen gas. The middle step is going to be the coefficients from the balanced equation. So we've got the oxygen has got 2, 1. Now we have how much again, is how much is grams for the methane. So we have okay, so methane is CH4, so that's 1201. 4 hydrogens is going to be 404. So we're looking at 1605 grams per mole. Okay, again, 3 steps. 3 steps. First step is to get to moles. Second step is ratio from the balanced equation. Last step is convert from moles to whatever we're trying to calculate. Every single time, 3 steps. Okay. So again, I recommend you go through the test, do the setups first, then grind out the answers after you got the setups all done. The setups are 9 points, the answers 1 point, or 90%, 10%. Okay, why don't you do the last one on your own here? Same reaction, burning methane and oxygen gives us carbon dioxide and water, and it's already balanced for you. So how many liters of oxygen if 5 grams of water is made? Remember, it's always 3 steps, always 3 steps. Still using OneNote? Yep, looks like it. You can put a grid down too,
Yeah.
if you do a view. You remember all this stuff? Everyone get the same thing that I got?
Yeah, I got that.
Does this make sense?
Yeah.
Yeah, 2/2 is fraction, which is
Yeah.
1. So you can include it in your calculations. You just say it's 1 and just ignore it.
Oh, I see what you're saying.
But some people like to include it just so they're complete. Okay. All right. So those are typical basic stoichiometry. Basic. This is when one given. I want to go over in a minute here. What if you have two givens? Things get complicated fast. You have two givens. All right. Are there any questions about any of these we've done? Notice again, 3 steps, 3 steps, 3 steps. Given to moles and the balanced equation ratio. Make sure what you're given is canceled always on the bottom. And then the last step is going from moles to what you're trying to calculate. All right. So let's get more complicated now here. Let's look at this problem here. This is the one I went over at the end of lecture last time. We have 15 grams of methane and 15 grams of oxygen gas. Okay, so that's 2 given. Yeah.
Sorry, can't read it.
Well, you have young eyes. Huh?
I was having trouble reading it too.
Speak up. I'm so hard. I'm such a hard person to talk to. You guys, just Ferguson. It's too small.
It wasn't impossible for me to read it, but it was just more difficult. That's all I'm saying.
Yeah, but you saw how long it took me to enlarge it. Okay. All right. So again, we have 2 givens. The problem is one of them will limit the product, the other will not. One is in excess. So you're gonna have to do 3 calculations now to figure out which is going to limit the reaction and determine the outcome. All right, so choose either one to start with. Okay, let's choose methane. And we're trying to produce, we're calculating oxygen gas. Okay, so we have the balanced equation here, and that's step 1. So we're going from methane to oxygen. And then the next time we're going to go from oxygen, excuse me, this is not, let me back up a second. It's not, we're making water. Going from methane to water, oxygen to water. I'm going to see how much water we produce. The one that makes the least amount of water limits the reaction. Okay, so, excuse me. So methane is 1605. Is that right? Flip it. Doesn't cancel. Grams need to cancel down here. So and where did I get 1605 from? Molar mass, perfect, from the periodic table, okay? 1 carbon, 4 hydrogens. Carbon's 1201, 4 hydrogens are 404, so we have 1605. Okay, grams cancel now. Okay, from the balanced equation, we have CH4 in the bottom, so it cancels, and water on top. Now we're going from water, moles of water to grams of water. So that's what, 16, oh, 1802, yeah. Moles cancel. Okay, so if we're looking at 15 grams of methane only, we're going to make 33.7 grams of water. Now, we're going to do the same basic calculation, only instead of starting with methane, we're going to start with oxygen, 15 grams of oxygen.
Two there would just cancel out.
I was telling her the same thing. 2 over 2 is the same as 1. So, okay. So, starting with oxygen, we only made 8 grams of water. Starting with methane, we made 33 grams of water. So which is it is limiting our reaction?
The oxygen.
Oxygen. Okay. So that's called the limiting reactant. The limiting reactant or limiting reagent is what gives us less product. Okay. So the next question is, well, if oxygen is the limiting reactant, what's in excess?
The methane.
The methane, the other one. Now, when this reaction goes, we're going to use up all the oxygen because we don't have enough oxygen left to use up all the methane. So we're going to have excess methane. How much excess methane? Okay, so now we need to figure out if we start with 15 grams of oxygen, how much methane is used? So the original 15 grams, we only used 3.76 grams. All the rest is in excess. So to find out how much excess, That's exactly. So we have start with 15 grams of methane minus. So what is that? It's 1123. Is that right? So we have a whole bunch of methane left over. So that's a typical limiting reagent. 24, you're right. That's what happens when you do stuff in your head. I was probably looking at the 7, and so I did 3. Okay, so does this problem make sense? So when you have 2 givens, you have 4 calculations to do. Okay, the first 2 calculations are going to, I know it's a whole page. The first one is going to be, first 2 are going to be determining the limiting reactant. Whichever was in excess, then we need to find out how much of that one's used. Then we subtract that from what you start with. 4 steps. And this will be the hardest one on the test. This one and the double replacement reaction will be the 2 hard ones. Okay, so that's basically what's going to be our test Tuesday. You'll have 1 of each minimum. Probably 1 of these. And at least 1 of the simpler ones, maybe 2. I'm designing this test to be an hour long and I'm going to give you 2 hours to minimize test anxiety. No one gets that, right? Okay, well, that's what I wanted to cover tonight. So you can stay and ask me questions, or for those of you who had 2 hours of sleep last night, like yours truly.
Are you gonna give us a packet on it or like practice?
There's a ton already.
On Canvas.
Yeah.
Canvas? Okay.
Do you know how to find everything in files?
I can show you.
I'm guessing go to modules, go to, or like, is it modules and files?
Both. Module calls from files.
Okay, so then go there, look for chapter or like
Go to unit 4. Yeah, go to unit 4.
unit 4 practice questions.
Just unit 4 on files, be all the files associated with unit 4.
Okay,
So
and then there will be worksheets there.
yeah, a whole bunch.
I have a question.
But it's stoichiometry last.
Would you be able to look over my resume? I created one,
Look over your what?
Yeah.
my resume. I
Oh,
created
sure.
a resume. I was with Pat and Billy's kind of giving me some tips, but I created it and I just want to see if you could look it over. if you have
Sure.
time.
So many
Could
people.
probably, you want me to just email you it or something? Or doing, this is pretty small on my phone, so.
Yeah, okay, just email it to me. And then, yeah, glad to look at it. Resume for just in general, or do you have a specific
So
job?
actually, I don't know if I already told you this, but I went to a career fair with my brother at Sac State, and I was talking to a couple companies, and they said that they're taking the interns that weren't even in 3rd year yet. So I thought that'd be a good opportunity to try to get an internship this summer.
Let me turn off the, I'm recording.
Yeah,
So-
oh, yeah,
so
oh, yeah.
Hang around for 2 seconds. Let me-
Oh, yeah, sir. My grandma.
Just a minute, let me,
Stop the recording.
yes.